Hi, I'm Pedro Alonso Campana, and together with Paul Prase and Tobias Schäfer, I am one of the authors of Predicting Dose Response Curves with Deep Neural Networks. In cancer screenings, one has the result of treating different cell lines with different drug molecules. A dose response curve describes the effect of each drug on each cell line as a function of the drug concentration. And the prediction of dose response curves has two main applications: predicting them for new cell lines or predicting them for new drug molecules. In the precision oncology setting, we evaluate our model using cell lines that were unseen during training, and on the drug discovery setting, we evaluate our models using unseen drug molecules. Furthermore, to ensure the quality of the dose response curves, we study three additional settings: smoothing, interpolation, and extrapolation, where the test set contains points from the curves that were not seen during training. Typically, to model dose response curves, different parametric models obtained from the Hill equation are used. These models assume that the effect follows a sigmoid dose response that goes from E0, the effect when the concentration of the drug is zero, to E infinity, the maximal effect achieved by that drug. Notice that these models have parameters associated to each of the drugs and cell lines, and this makes the prediction of dose response curves for new cells or drugs not possible. Furthermore, there are many dose-response relationships that cannot be modeled by these sigmoid models. For example, when a drug at lower concentration stimulates the growth of a cell line, but then at higher concentrations it kills the cell line, these models fail. For these reasons, we developed ARCANET, a neural network-based architecture. We developed two versions of ARCANET. The first uses vectors, fingerprints, for representing the drugs, and the second uses molecular graphs. The molecular graph-based architecture uses a series of graph attention layers to transform the drug representation. Both architectures uses vectors of gene expression to represent the cell lines, and they combine both representations into a single vector. Then, this vector is combined with the concentration and is transformed into a second latent representation where each of the hidden units is a Hill equation. And finally, with a multilayer perceptron, the architecture produces an inhibitory effect associated to each of the concentrations, generating a double response curve in the process. We studied the performance of our model in the smoothing, interpolation, and extrapolation settings, where, remember, the test set contains points from each of the curves. In these settings, we studied the performance of different flavors of the Hill equation, and we observed that our model consistently achieved better performance across mostly all datasets and settings. And furthermore, the fingerprint-based architecture achieved the best performance. We think that this is because these representations allows a model with a lower number of parameters that can be trained faster and more efficiently. We also studied the performance of our model in the zero-shot settings of precision oncology and drug discovery, and here we compared it to FAM4, Functional Random Forest, a method from 2021 that also tries to predict complete dose response curves. In the precision oncology setting and in the drug discovery setting, our model consistently overperformed FAM4, and furthermore, and interestingly, we observed that in the drug discovery setting, the graph-based representation achieves the best performance. We think that this is because this representation is more powerful, and this is crucial for the generalization to new molecules. As conclusion, we developed ARCANET, a neural network-based architecture that uses either fingerprints or molecular graphs for representing the drugs, and that uses vectors of gene expressions for representing the cell lines, and is able to predict dose response curves. We studied the performance of ARCANET in the smoothing interpolation and extrapolation setting, and we found that compared to parametric models derived from the Hill equation, the performance is better. We also studied the performance of ARCANET on the precision oncology and drug discovery settings, where we are generating zero-shot predictions of complete dose response curves, and we found that it achieves better performance than FAM4. And furthermore, and finally, when we compare both versions of our model that uses different representations for the drugs, we observe that the fingerprint-based architecture achieves the best performance across mostly all settings, but the drug discovery setting, where the graph-based architecture achieves the best performance. Thank you for your attention, and see you at the poster session, whose details are at the bottom of the slide.